Okay, so in Objective 3, what we're doing is being able to graph square root functions and cube root functions as parent functions and then do transformations, you know, good old-fashioned SRT transformations on it. So in this picture here, you can see, obviously, this tree has a cube root. That's pretty clever. And it looks like this was taken in Canada. So it's kind of an international lesson today. All right, so let's start off by just looking at the parent functions for the square root and for the cube root functions. So the parent function for the square root function is just f of x equals, or y equals, the square root of x. Okay, and its domain, well, remember we've talked about domain before. What kind of things do I get to take the square root of? Well, I can only take something that is 0 or bigger. So it says right down below, the domain has to be greater than or equal to 0. And the range, if I look in the picture, starts from 0 and then keeps going up. It goes up pretty slowly, but still goes up to infinity. But not beyond. Okay. Now, whenever you go to make the parent graph, you're thinking of convenient values that you can easily take the square root of. And those are the ones that you're going to choose for your key points. Like, for example, 0. I take the square root of 0 is 0. And then the next one would be 1, because the square root of 1 is 1. Then I would skip 2, I would skip 3, and then I would move to 4, because the square root of 4 is 2. And then the next one I would do is the next perfect square, which is 9, and it would go up to 3. But of course that picture doesn't show it. Alright, so now let's look over here at the other side at the cube root function, the parent function. So that's f of x equals the cube root of x. So let's talk about domain and range on that one. As far as the domain goes, is there anything you can't take the cube root of? No, you can take positive or negative or even 0, it doesn't matter. And if I look at the graph, I can see both up and down. It's all real numbers. So the domain and range of the cube root function is all real numbers. Now, as far as finding the key points for the cube root function, you're thinking of perfect cubes this time. Like, for example, 0. Take the cube root of 0, it's 0. Move over to x equals 1. The cube root of 1 is 1. And then you would skip 2, 3, 4, 5, 6, 7, 8. When you get to 8, what's the cube root of 8? It's 2. And that would be the next place that I'd put a dot. And then I'd do the same thing on the negative side. And as we've done before, we're just going to graph these kind of functions as transformations on a parent function. SRT transformations, our favorite kind of transformations. So let's look at this on Sketchpad. Look at each of these equations, and we're going to figure out what the a value does to our parent function, what the h and the k does. And here's a hint. It's the same thing that it has always done. But we're going to look at it specifically with those graphs. Take a look. Alright, so right here on this demo, this Geometry Sketchpad demo, which you can find on my website if you have the app on your iPad. Okay, so I've got myself the parent function graphed in purple there for y equals the square root of x. And then I have all of the parameters, the a, the h, and the k, that I'm going to do the transformations on. So let me go ahead and show the transformations. And it's already starting to be transformed right now because the a value is not at 1, it's at 0.72. And the h and the k values are at some other values. So let's just see again what these things do. If I stretch my a, if I make it bigger than 1, it is vertically stretching my graph. It's affecting the y values. It's multiplying all my y values by whatever that number is. So for example, if it is 2, it is multiplying all the y values by 2. Okay. If I make it between 0 and 1, it shrinks it down vertically. Makes it much, much thinner. And then finally, if I make it negative, it's going to reflect it. It's going to reflect it across the x-axis. Okay. And then the h and the k do what they do. Moves it left, right, and up and down. Alright, so let's look at the cube root one. So on the cube root one, same kind of deal. I have the purpley, here let's make this a little bit more symmetrical. There we go. The purple graph, all of the parameters that I'm going to transform this with, and the a value. Let's make the a value bigger than 1. What should we expect it to do when it's bigger than 1? Should stretch it out vertically. All right, and if I make it between 0 and 1, it's going to compress it. It's going to shrink it down. When I make it negative, it flips over the x-axis and turns in the opposite direction. Wah, wah, wah. All right, and then the h and the k, again, they do the translating left and right and up and down. All right, so here's a summary of those things. And as we said, the a value, it scales the function. It scales specifically the y value. So make sure that you make a note of that someplace, or remind yourself that this is always going to be a times the y values, right? If it's between 0 and 1, it's going to shrink it down vertically. Like if it's a half, I'm taking my y values and I'm making them half as big as they used to be. If that a value, we're not talking about positive or negative, but if the a value is bigger than 1, then I'm stretching that thing out vertically, and the negative sign just flips it over the x-axis. Okay? H and k do exactly what they've always done. H left, right. Inside the square root, it always lies to you, so this is a liar. And then the k, up, down, and it doesn't lie to you. It doesn't lie to you because it's on the outside of this. On the outside of the square root or any kind of parentheses. So let's actually graph one, right? So graph this function. I've got y equals 3 times the square root of x plus 2 minus 4. Let me go ahead and give you a second to get some graph paper. Go ahead, pause it, get some graph paper. All right, you got some? So the first thing that we have to do is graph the parent, and then we're going to detail ourselves the s, the r, and the t transformations for that thing. So for the parent function, we're talking about y equals the square root of x, right? So I'm thinking of perfect squares. So 0, square root of 0 is 0. I'd put a dot. The square root of 1 is 1. Skip 2, skip 3, go to 4. The square root of 4 is 2. And skip it all the way till 9, because the square root of 9 is 3. And so here's what the parent function should look like. Look at that. I was right on the money. You can't even see where those dots were. Okay. And now let's detail our S, our T, our S, and R, and our T. So our SRT transformations. D, D, and D. Okay, are we scaling it? Yes, we are. We are scaling this thing by 3. How do I deal with that? It's always 3 times the y coordinate. Am I reflecting it? So I'll look back here. The 3 is positive, so we're not doing any reflection. You might be doing some reflecting on the lesson, but you're not reflecting on the graph. Anyway, translating it, I've got a 2 there and I've got a 4 there. This 2 that's with the x, it's lying to you, so I'm going left 2, and the negative 4 means I'm going down 4. So you do that point by point on these points that we just put on there. All right, those key points. Let me switch colors so we have a different color for the actual function. How about blue? Sounds good.
Okay, so let's start at the origin, and let's do all these transformations on it. So 3 times the y coordinate, the y is 0, so it's not going anywhere. And now I'm moving it left 2, 1, 2, and down 1, 2, 3, 4. Okay, now move over to the next point. The y coordinate is 1. Multiply that times 3, so it's at 3. And now move it over to the left 1, 2 spaces, and down 1, 2, 3, 4. This thing is really getting stretched out. Okay, so now we're at the next point. The y coordinate is 2. Multiply it times 3. We're going to be at 6. Move it 1, 2, and down 1, 2, 3, 4. Right there. And then finally, the last one, the y coordinate is at 3. Multiply that times 3, and we're at 9. What the heck is 9? Right there underneath the function. Move it over 1, 2, and down 1, 2, 3, 4. Put a dot. Now let's see how close I was on each of those points. Must have been right on the money because I didn't see anything change. But here's the actual graph.
Okay, so then the last thing that I want to do is define what the domain and the range is. So the domain, if I look from left to right in my graph, the smallest number that I have here is -2, and it goes to infinity. So bracket -2 to infinity. For my range, the smallest number down below that I have is -4, and it goes up to infinity. So -4, infinity. All right then, so let's try that with a cube root function and then give you a chance to try it yourself. So on 13, I have a cube root function y equals negative a half cube root of x minus 2 plus 3. Let's get back to that lovely shade of red-ish. Okay. All right, so let's do the parent function on this one. So the parent function, of course, y equals the cube root of x. And I'm thinking of perfect cubes that I can put down on my graph. So one of them, I like to start at the origin. Maybe it's just me because the cube root of 0 is easy, it's 0. Then I go to 1, cube root of 1 is 1. And then I'm going to skip all the way to 8 because the cube root of 8 is 2. The next perfect cube would be 27, and that's 3. That is way off my graph, so I'm not going to do it. Now on the negative side, the cube root of negative 1 is negative 1. And the cube root of negative 8, there's 5, 6, 7, 8, is 2. And then connect the dots thusly. Thusly. There we go. Okay, look at how nice that, kind of like a stretched out S shape. So let's now detail our SRT transformations. S and my R and my T. So what am I S-ing it by? What am I scaling it by? That's the 1/2 that's right out front. So it's 1/2 times the y coordinate. Am I reflecting it? If I look back at the equation, it's got a negative sign in it. So yes, it's across the x-axis. I'm actually writing x-axis just because whenever you take pre-cal next year, you're going to be doing it across the x-axis and the y-axis. So you're going to have two different possibilities of reflection. Okay, and then finally translating it, the 2's lying to you, so it is right 2, and the 3 is not, up 3.
Okay, point by point, let's switch to parabola, this one. Okay, so let's just do this point by point. Why don't we start at the far left-hand side and just work our way across the graph. Okay, so I'm going to take half of the y-coordinate, so it's at 2, so I'm going to be at 1. Reflect it across the x-axis, so it's going to be at positive 1. And now move it right 1, 2, and up 1, 2, 3, and put a dot. There we go. Now move on to the next point. It's at, y-coordinate is at negative 1, so take half of it, it's at negative a half. Now move it, oh, no, reflect it, don't forget to reflect it. Now move it right 1, 2 spaces, and then up 1, 2, 3, so it's at 3 and a half. There we go. All right, and now we're at the origin. Take half of that, done. Reflect it, done. Now move it right 1, 2, and up 1, 2, 3. Okay, I'm at, I guess that's 2, 3 at that point. Now I just got 2 more points. I'm almost done with this one. All right, so I'm at 1, 1. Take half of the y-coordinates at 1. Reflect it. It's done at negative 1. Now move it right 1, 2, and up 1, 2, 3. And then finally, this last point, it's y-coordinates at 2. Take half of it. It's at 1. Reflect it. It's at negative 1. Now move it right 1, 2. It's at 10, and up 1, 2, 3. All right, let's see if we were right on the money for those dots. Looks like we were. I missed my half mark by a little bit on that one. That's all right.
So how about the domain and the range on this? Well, look, it stretches all the way across the graph. It's very flat, but still it's going to eventually take up the whole y-axis. So the domain and the range, all real numbers. All right, that was pretty fun, wasn't it? Love graphing. So here's your chance to graph a couple of these on your own. Take a look at these. So I've got a square root function, and then I've got a cube root function. Graph them, and then come back and see if you did it correctly. And then we're done. Okay, I hope you found that an enjoyable graphing experience. So let's first look at the SRT transformations for each of these. Voila. So on number 1 here, we are scaling this by 4 since there's a 4 out front, 4 times the y-coordinate. And since that 4 is negative, it's going to also reflect across the x-axis. And we're going to translate it right 1 and up 3. Okay, and then, well, the domain and the range will make a little bit more sense once we have graphed the thing. So you want to start with the parent function. So whenever I dot in the parent function, I'm thinking of perfect squares. So I'm talking about the square root of 0, square root of 1, square root of 4, and the square root of 9. Dash that thing in there. And then do the SRT transformations point by point on each of those, multiplying the y-coordinates by 4, reflecting it across the x-axis, and then moving it right 1 and up 3, and there you have your handsome graph. Okay, now it's obvious that the domain then is going to left to right, start at 1, and then move to infinity, And for the range, from the bottom to the top, lowest is negative infinity, and then it stops up here at 2. Okay, so let's look over here at number 2 with the cube root function. So the cube root, I'm scaling it by 2. I'm not reflecting it because it's not negative, and then I'm going to translate, this way. Left 4 and down 3, point by point. So whenever you dot in your cube root parent function, you're thinking of perfect cubes, like 0, 1, 2, and 8. And doing the same thing on the negative side. Dash that thing in there, and then point by point do your SRT transformations, 2 times the y. Move it left 4 and down 3. I actually ran out of room for the graph, but that's okay. It still looks pretty nice. And then, of course, domain and range for that cube root function, all real numbers. All right, that's it for this lesson on inverses and graphing square and cube root functions. So the inverses, we were able to find the inverse of a function and then graph those inverses as a reflection across the line y equals x, taking your x and y coordinate, flipping them. And speaking of inverses, the picture there is an Enigma machine, which the Nazis used during World War II to encode all of their secret messages. And in terms of encryption, inverses are pretty important, because if you send a secret message, whoever it's intended for needs to be able to work it backwards so that they can read it. Now, even beyond the Nazis, if you send any kind of secure information over the internet, it would be encrypted. All right, and then finally, graphing square root and cube root functions as transformations on parents. And that was even an application of inverses, because the square root function is the inverse of y equals x squared, the quadratic, as long as the domain is from 0 to infinity. And the cube root function is the inverse of the cube function. Oh, all right. Putting those pieces together. Okay, so here's your assignment, and there's Rowan saying the same thing he said last time. He's really wanting to catch on. Really wants to catch on. All right, I'll see you in class.